Mhm. Okay, we are live again. We have experimented another internet interruption, which is nonsense. And yeah, while designing the new image, look at this. How I'm going to organize this. While designing this image, episode 23 continuing on because of the internet interruption, and the chalkboard got closed. Mm, mm, okay, we were having a discussion of this Greek letter. So our fellows, English speakers say alpha, while in Mexico, Spanish speakers say alpha, or maybe I am wrong. Maybe it's the same. I don't know. Let's look for this because I wanted to say that at the end of the day, this is a Greek letter and maybe it's not pronounced nor alpha nor alpha or alpha, but if you are think, when we are when we are speaking Spanish, we have a lot of words coming from the English language, like internet. We say internet. Uh, we put the emphasis at the end, internet, and in English is internet. And what these we are saying these things, these words, and they are not these words are not from the Spanish. The Spanish, how can I say? This is the set of possible pronunciations of Spanish. Uh, uh, and maybe I don't know if this Greek letter whether it is alpha or pi. Uh, um, what's the other one? Epsilon. Maybe the famous one. You need to remember about your Greek your Greek alphabet. But the point is that I don't know how these characters are pronounced in the ancient Greek idiom or language. And if it is the case that at this point of time, just as we are using English words with modified pronunciations, maybe we should be pronouncing these things as they were pronounced hundreds of years ago. I don't know if I am being silly here. I don't know if there is if there are records on how these things were pronounced. Back in the day, I'm just an ignorant on the internet, and but I don't know if this should be the case for any given word from another language. You pronounce the word a little bit different, but I don't know if these things got these pronunciations. Uh, I was about to look about. I was about to look for this Spanish counterpart. And I was listening to Mick Ronson, a great guitar player, amazing guitar player. But then the internet got interrupted, and my happiness is never interrupted. I am always in a state of happiness. Sometimes I get angry or pissed off just a little bit points of the day. So no one can be happy the entire time. If you are happy the entire day, then you have some sort of, I don't know, maybe you want to take a look at your mind. No one can be happy 24 hours a day, the entire year. You know, you should cry sometime, feel some sadness for some, I don't know, not because someone is inflicting you damage or trying to teach you a lesson. That's nonsense. But you yourself maybe feel bad about uh, something happening in the world. Uh, maybe I don't know. You can't pretend to be happy the entire year. You will feel some other feelings. Like let's look for this alpha and letra. So the letter alpha for English. So it is alpha, as I was recalling, remembering. Oh, but here it says with pH alpha. So maybe there is more. So, so I don't know. This is from Gemini. Let's see. This guy is from Wikipedia. Okay, alpha. This Wikipedia thing is saying so. I suppose. But maybe there is more in here. Oh, there is this thing, this authority on the language. If this guy says something, then you should pay attention unless you manage to popularize a word by yourself, and they have to accept the thing you popularized, and they will include your word in their records. Uh, you know, it's up to you. Okay, so alpha, right, all right. Now let's go back to trigonometry. Let me show if I am live. We have this formula, uh, cosine of alpha, and then sine of alpha, being alpha a measure of some rotation. Then we said this thing works. We were happy yesterday. The thing worked. And then we said yesterday, we are not going to explore circles over here. And then today I said, let's do this for 10 minutes. And then the internet got disconnected. But we were not pissed off. We were not angry. We said, oh, the internet it's again disconnected, right? So one, two, three, four, five, six. One, two, three, four, five, six. And then we said, let's draw a circle. This will be a little bit hard to achieve. eventually. This guy. Oh, we went too fast. Too fast for love. Okay. So we have one, two, three, four. It is not a scale. Look at this. How big this is. Six. Of course, this is not the center of the circle. So anyway, so the radius is, oh my God, we say two, and look at this, two is here. So there was a circle. So there was a circle. I we say one, two, oh, why? One, two, three, four, five, six. One, two. Let's say this is two. One, two, three, four, five. Okay, we are missing the thing. Mm, let's do something else. We want this to be three. We want this to be three. Therefore, this should be four. This should be five. This should be two. And this should be one. In order for this to be one and this scale, most likely there will be a, this will be the x, you know, the origin. Then we do this. Then we can go like this. So the radius will be three. One, two, one, two. This is the radius. Three, four, five, six, seven, eight. One, two, three, four, five, six, seven. Okay, so the radius is two. Here's our fellow. So this guy is at 2, 3, and we are going to perform a rotation of 90 degrees. So we are targeting this part. So it will be 0, 5. We want this to happen. 1, 2, 3, 4, 5, 0, 5. Okay. Hmm. So let's use this. So the rotation is 90 degrees. Let's use our calculator. This is 0. And with this, everything goes to 0. Now, sine of alpha this is 1. Plus times 1 times radius. 1 times radius, which is 2, is 2. 1, 1 times radius. This is 2, but we need for this to be 5. How can we transform this? Can we add the y component? It's there. It's 3, and it's the missing part to achieve 5. So we can say we can modify if the circle is not at the center. We can say plus y. So it will be r times sine of alpha plus y, the original y, that will give us 5. Now let's suppose the circle is move a little bit more over here, and it's 5. Then we are targeting for to 7. 2 times 5, 2 plus 5 is 7. So this thing is working. You are adding the y component, right? Let's suppose this you are moving the circle downwards, and now it's here. This same circle is now here. Sorry, here. So, so now this point is at uh, 2 minus 3, and we are targeting 1 minus 1. So it will be minus 3 because of this oh, now I'm confused. Let me draw this thing. The circle will be not accurate. Accurate. So now we are here. Now we are here. Now we are here. And this is oh, this point. Maybe this is a different point. Yeah. We this if this is another circle, we need to forget about this component. So this is 2, but it's now minus 3. And if you perform a rotation of 90 degrees of this point, it should end here. So we are aiming to 0 minus 1. Remember, the radius is still r. The radius is still r. The radius is still 2. So this will be 0. Cosine of 90 degrees is 0. Um, for here it will be 1. Sine of 90 degrees is 1 times r minus 3 plus radius plus 2. This is minus 1. So we end here. Right, so this thing works. So if the circle is not centered at the origin here, and you will be playing with the components if it is, you should be careful because if you try to make let's suppose you say the x component will also be, you will also add, uh, like the radius, then you will end at 2, 1. You will end here, and you don't want that. So this adds some complexity to the formula. You will want to check if it is moving on the y-axis or if it is moving only on the if the circle is located on the x-axis, whatever terminology they use. And if the circle is over here, maybe you want to add then the the two coordinates, right? Like this is 8, so this means this will be 8, 3. We're going to reach this, which will be 6, because it's the radius 2, 6, 5. Then you will have the same rotation. This will be 0. Cosine of 90 degrees is 0. But we said that if the circle is not only on a given axis like this or here, it's now on in the middle, if you will. It's abroad. uh, and then you will have 0 plus 6, and you will end here. 0 cosine of 90 degrees is 0 times the radius is 0 plus the x component un is still at 6. And then sine of 90 degrees is 1 times 3 is 3 plus the radius plus y. We say y. We said y. We don't say the radius. So maybe this is 6. So maybe this is 6. 3, 4, 5. So this is 6. Oh, no, yeah. No. So this is 3, 4, 5. What do we did? What? We need to come back here again. So this is uh, 0, 3, and this is 0, 5, 4, 5, and uh, we didn't add this guy. We add this radius 2, so we ended on 5, and here we added the radius um, um, minus 3 plus 2 is minus 1. So this should be 5. This should be 5. This should be 5. So sine of 90 degrees is 1 times the radius is 2. So again, this is wrong. Let's go back again over here. Uh, Radius 2. The sine of 90 degrees is 0. So this stays in 0 if you are multiplying by 2, which is here. And sine of 90 degrees is 1 times 2 times 2 uh, times 2, which is the radius. Radius it's 2, and we say that we should be adding the sine of 90 degrees is 1 times radius. This is 2. In order to achieve 5, to reach 5, we ended adding 3, and this thing worked. Now we move, this is another circle. We added this. Where is the, we added this guy. 5 series. 1 times 2. 2 plus 3. We ended here. But now this thing got we have this 2 minus 3. This, and we want to achieve 0 minus 1. So by cosine of 90 degrees, 0 times radius, 0. This is great. Now, sine of 90 degrees is 1 times 2, which is the radius. The radius is still 2. What we want is number, but we said that we should be adding this. And then we reach this point. Okay, so we are cooling here. Most likely the same principle applies in the x-axis. Uh, if you instead add the x component of the coordinate. But now we are here. This is 6. In order for this to be h3, this has to be 6. 6, 3. The origin is at 6, 3. Let us see if the origin will have with something. So we are taking note of here. And now cosine of 90 degrees is 0. So everything goes to 0. And what we need to be on 6. So we can say that we can add the x component of the origin here. And maybe we can experiment down here. We are stating that well, these formulas are because of the 90 degrees. Maybe for the 180 degrees, this thing should not work. There is a lot of experimentation that should be done here. But we have the basis, right? We have the basics. And now we want to achieve or six, seven, oh my God, five again. Yes, we want to achieve five again. We want to achieve this. So sine of 90 degrees is 1 times the radius, which is 2. We have again this 2. And you can add this the y component. And then you will end at your desired 5. So the left thing to do, uh, remaining things to do is to see if this thing is going to work here or here or here, and to try another angle rotation. But it's too late. Yes. So we elaborated on this even when we said yesterday that we shouldn't be doing it. So you can do this on your own if you like it. I will do it, but for the sake of my own edification, not 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 live. I will share the results with you in 5 minutes. Uh, but now let's do something very quick before saying goodbye for today. So the thing work on this coordinate system. But you should look how this screen is. This is nonsense. And there is some circle over here. And we are able to rotate this fellow over here. So all over the place. But in the computer screen, uh, we have uh, um, so this is 0, 0. So this is 0, 0. But now in the screen, and this thing works. We have the formula. But now in the screen of the computer, this is 0, 0. Well, we should be doing this tomorrow. Okay, this is 0, 0. That only means that here, this thing is the same color. Mm, Don't worry. My God, why? I suppose that's the case. Now I'm going to delete this thing. It's a little bit let's draw the straight edge. Well, here's the straight edge. Remember, this is 0, 0. Let's localize the quadrants for you, or for me. Oh my God. Let me remind this. This is the first quadrant. This is the second quadrant. This is the third quadrant. And this is the fourth quadrant. Now let's localize these things. So this is the first quadrant. This is the second quadrant. This is the third quadrant. And this is the fourth quadrant. Right? Uh, I can't believe how these guys managed to. And it works. The computer graphics is quite a thing. And the thing works even if the system of coordinates are like this in a lot of software. Not only on the web browser, on the canvas in the web browser, in a lot of software, you will find that this is the case, that it is modeled in this fashion. And I don't know how these guys, I would like to see some document in which how the design process went for this, the thinking, because it's, if they decided in this fashion, it's because it is very convenient given the constraints of the computer. The guys in the past were insanely creative, as this Steve Jobs said, insanely great. So these guys were very creative, a lot of wit. And you will not believe their designs, uh, and you will, and you we will be able, you will be able to learn a lot by seeing their decisions in design, on designing these things in the past. So given this, let us take a look at how can you make a little bit of sense of this? Maybe they took this, they're looking at this from the above, this on the plane. This thing, this thing, look at the mouse. You're looking at this from above. This thing is in a plane for you. It seems that these guys say did. What it seems to be is that Imagine this having some handlers over here, or maybe here. This is like a toy. These are some handlers. This is a plastic toy. What they did is you're looking for a bubble. They move it, they rotate it. So the one ended. It would be great if I do some animation in Blender with this. If they want, if they want, it seems like a reflection, not a rotation. Not reflection. Yes, reflection. It seems like a reflection. There is a operation in geometry called reflection because look, one ended here, two ended here. It's like inverted. This uh, uh, reflection symmetry, point of symmetry. I don't remember. I don't remember the correct term. I will read the book again. Again. So it seems more like reflection instead of the rotation that I said to you. There is no way for this. There is no way that you can rotate this thing and in this fashion. There is no way you can apply a rotation to this image to end like this. So it is a reflection. Well, I don't rem I have my it's not here. Uh, Tomorrow I will I will enter with reflection and then go directly to the code. Now it's time to code again because here is the strategy. Yeah, another color. Maybe this. So you have this point over here. Remember, let us locate this same point in here. It's here. The strategy is here. So this is the point. And you want to arrive, you want to land this point, to rotate this point over here. So the straight edge will be like this. Okay. So this point will end here, which is what they do. If you apply a 90 degrees rotation, this is what happens. But now, after all the journey that we did, all the detour of trigonometry that we did, it is time for us to be able to have some straight edge down over here, having this point, because we are going to rotate at the center. It will not be straightforward. Okay, and this is the handler, if you wish, the origin. We should be able to draw this thing here and move this point, maybe this point, maybe this point at 90 degrees or any other rotation. And now it will be like this. If we do that, we deserve a soda. Okay, so have fun. It's time for us to leave because, um, yeah, same excuse. I'm going to play the guitar. But yeah, this is the. We're going to repeat this drawing tomorrow and more drawings as we do the code, as we write the code or type the code. type the code maybe. Uh, since this thing we are rotating here, we should be able to negate the entire quantity. So to take into account this, a lot of experiments needs to happen. I hope you guys enjoy it. I'm not going to save this image. So people were seeing this thing. Okay, bye. We didn't set an alarm for today, but tomorrow we are going to set an alarm. I don't want to promise you any number of hours. Okay, thank you very much. Bye.